Hi, we're graphing logarithmic functions. So remember from yesterday that the mother function to a log graph has an asymptote at x equals 0. Our graph goes through the point 1, 0, and then whatever your base is, so b to the 1, okay? So let's call that the base. Okay, so we can see that the domain of the mother is domain is x is r greater than 0. Okay, so when I look at the domains of each one of my log functions, I need to take the input. This part here needs to be greater than 0. So I'm going to set x plus 3 has to be greater than 0. Otherwise, I can't evaluate. So I'm going to go ahead and solve minus 3. I get x is greater than negative 3. So as long as I plug in x's that are greater than negative 3, then we are good to go. G of x, again, we're going to take the inside part, x squared minus 1, and set it greater than 0. I'm going to add 1 to both sides. So I get x squared is greater than 1. And then I see that I have an inequality with a root. So I'm actually going to change this to an equality to get a boundary point. So I get x has to equal plus or minus 1. I'm going to go ahead and set up my number line. And I'm going to test. So let's test 0 first. I'm going to plug it in right here. So 0 squared minus 1 is greater than 0. Negative 1 is greater than 0. That is false. Over here at 2, I get 2 squared minus 1 is greater than 0. 4 minus 1 is greater than 0. That's true. Let's test negative 2. So negative 2 squared minus 1 is greater than 0. Again, we're plugging it into our original inequality that we set up. We get 4 minus 1 is greater than 0. Again, that's true. So I have my points, let's see, open circles on our boundary points, and to the right and to the left of our boundary points. So my answer is x's have to be greater than 1, or x has to be less than 1. Again, different intervals, so different sets of interval notation. All right. Lastly, we have the ln of x, ln of absolute value of x. So my input is the absolute value of x has to be greater than 0. And I remember that anything I plug in for x is going to, when I take the absolute value, it's going to be greater than 0, except for one number. X cannot equal 0. That's the only one that's not greater than 0. So those are our domains. Next, we're going to use the function negative ln of x minus 2 to determine the following. We're going to graph first. I always start with negative 1, 0, and 1 for my mother function. It's the inverse to an exponential, so I put what I would have put in the x, I put into the y. And then I'm going to evaluate e to the y because that's the base of my log function. Okay, this is still y. So e to the y is equal to y. So now I'm going to go ahead and plug these in. I get 1 e to the negative 1, which is 1 over e to the 0, which is 1, and e to the 1, which is e. So I'm going to go ahead and graph in these ordered pairs. I'm going to assume e, remember, e is about equal to 2.718, I think. Let me double check that. E. Yeah, 2.718. Okay, so we're going to go our asymptote for a mother function. So we're graphing the ln of x, not the ln of e. Okay. I always have a point at 1, 0. That's that guy. I have a point at E, so 2.7, comma 1. Okay. See if I can hit the go. And then negative 1, or 1 over 2.718, comma negative 1/2, so something like that. And I'm going to graph that in. Okay, so that's like that. Okay. Then what we're going to do is we're going to apply the vertical and the horizontal stretch. So in this case, I only need to take my y values and multiply by -1. So I'm going to start with 1 over e, 1, and e. The x's don't change. There's no multiplier here in front. So next, we're going to take each one of our y values and multiply them by -1. So -1 times -1 gives me +1. 0 times -1 is 0. And 1 times -1 is -1. So each one of these points is going to get flipped, basically. So my asymptote doesn't change. I can vertically flip it and it won't change. My point 1, 0 doesn't change. At 1 over e, I'm now going to go up 1. And at e, which is 2.17, I'm going to go down 1. So you can see that we've vertically flipped. Ooh, that was really bad. Okay, lastly, we're going to take this table and we're going to apply this -2, the horizontal translation. So the only thing to remember is when you're affecting the x's, it's opposite. So instead of subtracting 2, I'm going to add 2. That's right. We're going to add 2 to each x value. Okay, so we're going to have 2 plus 1 over e, 2 plus 1, which is 3, 2 plus e, which is 2 plus e. Okay, the y values don't change, so 1, 0, -1. The other thing that changes here is my asymptote. It's going to move over to, we're going to add 2 to it as well, so it's going to move to the right 2. Okay, so I'm going to move my asymptote to the right 2, 1, 2. And then everything else moves along with it. So from 1, 0, I'm going to move it over 1, 2 to go to the value 3, 0. I was at 1 over e, comma 1. Now we're going to add 2 to that, so I'm going to move over 1, 2. I was at e, comma, so 2.17, comma, -1, so I'm going to move over 1, 2 places. And that is the graph that we just graphed. So x equals 2 is our asymptote, and then each one of our points got shifted over 2. Okay, so looking at our domain of f, I'm going to erase this. We're going to do all of our features now. So algebraically, we're going to do our domain. We take the inside, x minus 2, and set it greater than 0. We add 2 to both sides, so we get x is greater than 2. For the next one, looking at the domain and the range from the graph, so I'm looking at this graph right here. I can see that my y's are y is equal to all real numbers, and I should put x's are greater than 2. The vertical asymptote at x is equal to 2. Now we're going to go ahead and graph in the inverse of our function. So what we're going to do is we're just going to reflect it over the line y equals x, or remember each one of these points are just going to be moved. We're just going to reverse them. So the inverse, I'm going to make the table for the inverse down here. X and f inverse would be take my y's, and they're going to become my x's. So 1, 0, negative 1. Take my x's, and they become my y's. So 2 plus 1 over e, 3, and 2 plus e. And we can get a decimal equivalent here. So 1 over e plus 2 is about 2.37, and 2 plus e is about 4.12. So I'm going to graph those in. I'm going to go 0, 1, 2, 3. 1, comma 2.3, and negative 1, comma 4. 4, a little more than 4. And what it looks like is this. Oh, and we had a vertical asymptote at x equals 2. So our horizontal asymptote, because it switches, is going to be at x equals, not x, horizontal is y, equals 2. So I'm going to set it up right here. Our graph goes without bound. It gets really, really close to the to the horizontal asymptote, and then it goes without bound going upwards. That's it. All right, so from the graph, we're going to figure out the domain and the range. So I can see that the domain is that x's don't stop, so have to equal all real numbers. The y's, they have to be greater than our horizontal asymptote, so at 2. And then finally, we're going to figure out the inverse algebraically. So our function is f of x is equal to negative ln of x minus 2. So to find the inverse, we switch x and y. So x is equal to negative ln of y minus 2. And then we solve for y. So we want to get ln by itself, but I have this pesky negative. So we're going to go ahead and divide both sides by negative 1. So I get negative x is equal to the ln of y minus 2. All right, so now we need to get into exponential form. So we're going to snail. So the base is e to the negative x is equal to y minus 2. And then we got to get y by itself, so add 2. So y is equal to e to the negative x plus 2. And that is f inverse of x is equal to e to the negative x plus 2. So this is really how we should write it. And that is it.